Okay, well, thank you very much for having me. It's a pleasure to talk. It's nice to see a good turnout. I come from the field of particle physics, and I've been doing a lot with machine learning, both in the context of particle physics and then also, more broadly in the physical sciences, and in the effort of sort of trying to abstract away from the specific details of particle physics, we've come across this, I think, very nice framing of how machine learning can be used and how it's sort of, broadly relevant to what's going on in science and engineering fields. I've been, some of these slides that I'll be showing are in, connection with a number of collaborators. In the last few years, I've been working with a mix of computer scientists and mathematicians and various domain scientists, and it's been a lot of fun. So I just wanted to call them out here. So I'm going to start with this kind of, relatively straightforward claim, I guess, which is that science is replete with high fidelity simulators. We have simulators that describe, particle physics interactions at the, subnuclear scales. We have simulators for, neuronal activity, epidemics, gravitational lensing, the evolution of the universe, imaging of black holes, molecular dynamics, sort of you name it. And the expressiveness of programming languages has, allowed us to develop very complex and very high fidelity simulations, meaning that they describe the data, accurately. And the power of sort of modern computing allows us to generate a lot of synthetic data from those simulations. And the ability to generate a lot of synthetic data, you can imagine, is going to play very well with machine learning. But the problem with these kinds of simulators is that they are not well suited for statistical inference. And I'll make that more clear in just a second. So here's a kind of abstract framing of the problem, is that I can think of my simulator as this kind of predictive direction. My simulator has some parameters, here I call theta or nu. And then I run the simulator, which might either be deterministic or intrinsically stochastic. And then it's going to output some synthetic data that is in the same space as the observed data. And so the way I think of the simulator is it's sort of implicitly describing some probability distribution over the observed data given those parameters. And the parameters of interest are usually the ones that we would like to infer that might, for me as a particle physicist, might be like the mass of a new particle or how strongly it interacts with other particles or something like that. And the nuisance parameters might describe things like my experimental apparatus, like I don't know the calibration constants perfectly, and things like this. And so I don't necessarily care about inferring the nuisance parameters, but they will have an impact on the distribution of the data. And in addition, inside of the simulator, there might be lots of other, random variables, which may either be, physically meaningful, or they might not be physically meaningful. But if you think of the physically meaningful ones, they're maybe they might describe some microstates of your system, but the things that as an observer, I'm not able to see. So those are usually referred to as latent variables Z. And so then, so this is the kind of predictive direction, sometimes called like forward modeling or a generative model for the data. And then given some observed data, I would like to turn that around and invert the process and try to say something probabilistic about the parameters that I would like to infer. So that's this kind of inference direction. And this is the part that's difficult. So the simulators might be very accurate, but this inference problem is hard. So, so what I'm pretty excited about, I'd say, is that given how omnipresent these simulators are, and how you have this kind of common difficulty that for instance, the interaction of all these low-level components inside your simulator leads to some sort of intractable inverse problem. The thing that's pretty cool is that the developments in machine learning are really giving us now the potential to be able to sort of effectively bridge the microscopic macroscopic divide between microscopically what's happening in the simulator and the parameters that you're using to describe that mechanistic model, and then the macroscopic phenomena that you're observing directly. And so in practice, these machine learning techniques are giving us some sort of effective statistical model of the macroscopic or emergent phenomena that are still tied back to the low-level microscopic reductionist model. And if you can do that in any kind of systematic way, that's going to be very important for science. So just to make it a little bit more specific in the context of particle physics, we have a fundamental theory that describes the fundamental particles of nature, and when here it is. This is the so-called Lagrangian of the standard model. From that, you can use pencil and paper techniques and things like Feynman diagrams to try to imagine what would happen when two particles scatter off of each other and produce these other particles. This is a Feynman diagram. This is something you can do with pencil and paper, but it's not the end of the story. After that, these particles, especially if you have things like quarks and gluons, they will radiate more and more particles. And that process is sort of understood locally what's happening, but the overall process becomes very complicated. And then there are other things that happen. This is particle physics, so you get things like quarks and gluons recombining into things like protons and neutrons and various stuff like that. And that's what these dark green blobs are. And these are now physical particles that come flying out into our detectors. And so we also have to simulate how those particles are going to interact with the detector. And that includes this, microscopic, tracking of, like say charged particles going through material and ionizing along the way, and how the electronics respond. Conceptually, this detector simulation is telling us a probability of some sort of detector response given those incoming particles. If you shot the same incoming particles in a second time, the detector response could be different. That's why it's a probabilistic story. And the implementation of this is through some kind of, Monte Carlo type algorithms where you're following particles along and you sort of throw a dice and decide whether or not it's going to decay or not, or, deposit some energy or not, according to some well-known microphysics. The consequence, though, is that the evaluation of the likelihood for the final observation is something that's totally intractable. If you wanted to know what's the probability of getting a certain energy deposit in a part of the detector, I would need to integrate over all the possible histories that could do that, and that's just not tractable. And so this motivates a new class of algorithms for what's commonly referred to as likelihood-free inference. I've started to call it simulation-based inference. I think it's a little bit more descriptive, but which only requires the ability to generate samples from the simulation in the forward mode. So this is a common theme in many domains. So there, going back to around 2014, there were some workshops held in connection with the big machine learning conferences talking about a technique called approximate Bayesian computation, or ABC. And they talk about it as a class of computational statistical methods for inference under intractable likelihoods. So that's what we're talking about. It talks about how it's useful in systems and population biology, computational neuroscience, computer vision, healthcare sciences, etc. It's also very relevant for particle physics and astroparticle physics and things like that as well. Now, the way this approximate Bayesian computation algorithm works, roughly, is that you're imagining that you have some sort of prior distribution over the settings of your simulator. If this is done in a Bayesian context, so you have to provide that prior. Then you sample a parameter point from your prior, that's theta, and then you run your simulator and you get some synthetic data d prime. And then you are basically going to want to compare the simulated data to some observed data, but how are you going to do that? In practice, usually you calculate some summary statistics. So you might have very complicated data and you kind of boil it down to a few quantities that really characterize your signal, and that requires some domain knowledge. And then there's this notion of some sort of distance between the observed, the summary for the observed data and the summary for the synthetic data. And if it's close enough, then you sort of accept this parameter point theta and you add that to a list of samples. And what that will end up doing is sampling according to the posterior distribution. Now, this is kind of nice and simple, but it's got various problems. I mean, the summary statistic can lose some information. This distance measure is quite ad hoc. The fact that there's some tolerance here means that it's only an approximate inference method. And so, it's been used quite a bit, but it's not the ideal algorithm. In particle physics, we've been doing something fairly similar. It's usually not in a Bayesian context, but we also run the simulators. They're very complicated data sets, and we usually are able to then summarize these very complicated observations into just a single quantity. And that's what this like horizontal axis of this histogram is when we were, say, searching for the Higgs boson. And this bump right here is like the evidence that we are actually making the Higgs, the fact that there's more events observed than you would have expected from other processes. But the point that we were able to come up with a good variable here to histogram basically means that we had a good, powerful summary statistic. The problem is that this approach does not scale if the data or the summary statistic is high dimensional. If you have a very high dimensional summary statistic, you can't fill high dimensional histograms. And in this previous approach, the chance that you're close by to the synthetic data is close to the observed data becomes just incredibly small. So this approach doesn't scale well. Now, right around the same time in July 2012 that we discovered the Higgs, it was also the kind of watershed moment of deep learning. And so, as I went into sabbatical, I was thinking about how can we take advantage of deep learning to try to address this kind of problem. And in 2017, there was a workshop that was really held kind of explicitly on this connection. So it's talking again about how several real world phenomena are better described by simulators that do not admit a tractable density. That's the same point. The likelihood function is intractable. And then here you see, it's mentioning, it's used, for instance, for particle physics. And then they connect it to various hot topics in machine learning, like generative adversarial networks or GANs, variational inference techniques, this approximate Bayesian computation that I was just describing, and then things like two-sample testing, which is basically like hypothesis testing, and I'll say a little bit more about that. So we recently, just this last year, wrote a review on this subject, and we called it the frontier of simulation-based inference. And we sort of have this kind of, conceptual diagram of, on one axis, you have essentially the simulator cost and the dimensionality of the thing that you're trying to infer, whether it's the parameter vector theta or the latent, the latent variables z. And then on the vertical axis, essentially the dimensionality of your observed data. And so the traditional techniques that had been developed basically sat kind of down here in the bottom corner. They didn't work very well if you wanted to do inference on high dimensional data or if your simulator was very expensive, and they didn't work well if your data was high dimensional. So machine learning is sort of helping us move in the direction of higher dimensional data. I'll say a little bit about integration and augmentation of the simulators themselves to try to improve things. And then there's the idea of active learning, which I will only kind of allude to. I don't have enough time to sort of get into that, but about essentially makes the use of the simulator more efficient. So in this review article, we sort of break down approaches into, broadly two classes. One class is where you use the simulator directly for inference, but you need to do it in a much more efficient way than some sort of naive approach. And so that encompasses approximate Bayesian computation, but more sophisticated versions, which involve things like universal probabilistic programming, which I'll say a bit about. And the other approach is that you try to essentially learn the simulator and have some sort of surrogate, and you'll use the surrogate for inference. And that includes things like generative adversarial networks, variational autoencoders, the likelihood ratio trick, normalizing flows, and autoregressive models. So this is where like deep learning is really, shows its power. So also in this review, we have these like flow charts, which I'm not going to go through carefully, but they all sort of have a simulator. That's the yellow box. They all have data. That's the blue over here. There's also always has some sort of comparison of the two to get either a posterior distribution or a frequentist like confidence set. And so in this set of flow charts, the top row are essentially the first class of methods that I discussed, where you're using the simulator more directly, like approximate Bayesian computation and probabilistic programming. The bottom row are these approaches that have some sort of surrogate involved, where you're using like deep learning to approximate the simulator. Some of these techniques use unsupervised learning, some of them use supervised learning, and some of them involve an augmented simulator, where you take the domain specific simulator that you have, and you might need to add some extra capabilities to it to take advantage of these new ideas. So the first one I'll describe briefly is this probabilistic programming approach. So here's some code. We're not going to go through it. It sort of looks like a scheme type of language. And what it's doing is it's just randomly drawing some number of bumpers. That's these little green bars. Some number of bumpers according to a Poisson distribution. And then it's uniformly placing them with X and Y coordinates. And then once they're all there, it runs a physics simulator that just drops these balls and lets them deterministically, do what they would do, and they're bouncing around. And you notice that over here, there's a little box, right? And the balls don't land in the box. And these are 3 example runs of the simulator. And because it's got random numbers involved, it's describing implicitly a distribution over the possible executions of this program. And this is just 3 samples from, since the prior distribution of the executions of this program. But I can also do Bayesian inference where I say, well, what would executions of this program look like conditioned on 20% of the balls landing in this box over here on the right? And then we can run it again, and you see, other arrangements of these bumpers where you get this kind of very unlikely outcome where the balls do happen to bounce and make it into the box on the right. This last one's pretty fun to watch. Yep, makes it, okay. So, sampling from this posterior distribution, if you just did it through naive approaches, would be very inefficient. And so part of the cool stuff with probabilistic programming is how to make this more efficient. So recently we've done some work where instead of having to work with kind of specialized languages for this kind of research, we can work with like normal simulators, domain-specific simulators that are written, say, in C++. So we're using standard simulation software that's used in particle physics, and we introduced a protocol where an external process can essentially control the random numbers. And so that external process is then what's called an inference engine. And it essentially tries to bias the execution of the simulator to try to get a particular observed outcome. And it biases the simulation in a particular way that you can account for and correct for, and that allows you to do this kind of Bayesian inference. So, so this PyProb technique allows you to it's kind of language agnostic and allows you to extend existing simulators. And this work was nominated for Best Paper at Supercomputing 2019 and involves some very, very, very large neural networks to try to do this importance sampling. And I just point you to this PPX tool, which is the kind of protocol for controlling your simulator. More recently, these things have been used in the context of epidemiology and population genetics. Here's a handful of papers. And you can imagine that it's not hard to write a simulator that describes, agents out there in the world interacting with each other that might get, that might be infected and spread the disease or, recover or die or something like that. And so, but being able to control that simulator to try to, match some observational data is what we're providing with these tools. Okay, the next approach I'll talk about is down here on the bottom, which is one of these deep learning approaches where we're going to use a surrogate to try to approximate essentially what the simulator is doing, but instead of trying to approximate the likelihood function or the probability of getting a certain outcome directly, we're going to try to approximate a likelihood ratio. And I'll clarify what I mean by that. So schematically, this is the picture. We have a simulator over here on the left. The simulator has some parameters theta. I'm going to choose those parameters, run my simulator. There might be all sorts of latent variables inside of my simulator that I'm not going to observe. And the simulator outputs some synthetic observations. And I'm going to use the neural network where the neural network is not only going to take observed data as input, it's going to take the observed data and the value of the parameters used to generate the data as input. And what it's going to try to do, it's not going to take in observed data and try to predict the parameters. It's going to take the parameters as input, and instead it's going to try to approximate a likelihood ratio. So that's the likelihood of the data for this value of the parameter compared to some other reference point. And once you have that likelihood ratio, then you can scan the parameter theta, the input here, and then you can do, for instance, statistical inference. So you can, say you can find like the best fit point, like the maximum likelihood estimator, but you can also have like principled error bars and draw contours and things like this. So this fits more into like a scientific workflow where you want to make parameter measurements with calibrated uncertainty statements. And so this is a sort of two-stage procedure. The first, you need to learn this surrogate, and that process is amortized. It's expensive upfront cost. And once you've done that, then the inference is fast. So here, how does that work? Well, there's a few different techniques, but one of them just uses the simple idea of a binary classifier. So if you imagine I have red dots and blue dots, and let's say that the blue is from a hypothesis, the signal hypothesis H1, and the red dots are my background hypothesis or null hypothesis H0. And I don't know the probability distributions explicitly, but I can sample from them. So I can get red dots and blue dots. Symbolically, I could consider this loss function or loss functional, where S is some classifier whose goal is trying to say that if the data point is a red point, I want to try to output something close to 0, and if the data point is a blue point, I want to output something close to 1. And so you see the loss function says if the data comes from H1, it should be close to 1, and if it's not, there's a penalty. If it's close to, and vice versa for H0 and 0. And so this is a particular loss function. And if you use calculus of variations to find the function that minimizes this loss functional, it's this. This is the Bayes optimal classifier. And that's 1-to-1 with a likelihood ratio, which if you're a frequentist, you know from the Nyman-Pearson lemma is the most powerful way of doing a hypothesis test between these two hypotheses. So this is like a very principled thing to shoot for, and this is kind of a means to an end. This is one way of learning a function that is 1-to-1 with the likelihood ratio that we would like. And then this objective is something that involves these integrals over these distributions that we don't know explicitly, but we can approximate that with samples. So if we have samples, say balanced samples of red dots and blue dots, and we label them 0 and 1, then this loss function, just the simple squared loss function, will approximate this kind of idealized loss functional. So that means that in practice, we can approximate this likelihood ratio. And that example that I just gave was for just two discrete hypotheses, but you can kind of lift that to a parameterized setting where instead of just having two binary hypotheses, H0 and H1, I can think of having say a simulator with some free parameters theta, and I just pick two values of those parameters and call them theta naught and theta 1, and I generate data from each of them, and then I can learn the likelihood ratio between those 2 points. And instead of doing that like for every possible pairing of theta naught and theta 1, instead I can create a neural network that I call a parameterized classifier that depends on the data, and then the two values of theta that you want to compare. And oftentimes you just fix one of these to be some reference, so it doesn't explicitly depend on the sort of alternate. And so now you can scan across the parameters and evaluate the likelihood ratio continuously as a function of theta. So this was the idea that I just explained, and that was the first sort of set of papers that we had on the subject. And then we realized that we could do something smarter, and we could augment the training data by reaching into the black box that is the simulator. We can extract some other augmented training data that we can use as part of some new loss functions, such that when we minimize those loss functions, we come up with a good approximation of the likelihood ratio, and we can do that with orders of magnitude less training data. So I'll just give a quick feel for how that works. So here's an example of a simulation of just like dropping balls through a lattice of nails, and you see them bouncing around. So the path that you take through this lattice of nails is like a latent variable, and where you land is like the observation X. And your goal is to try to understand this distribution of P of X. And the theta parameters you might imagine are changing, like the locations of these pins or the separation between them, or maybe the location where you first drop the balls or something like that. Now, the idea here is that here's an example of two paths through this lattice of nails that both end at the same location. So the thing that you would like to know is the probability of the observed data given the parameter theta, but to calculate that probability involves marginalizing over all the possible paths through the simulator, and that's this intractable integral that in practice you're never going to be able to do. But what you can do is augment the simulator so that every time it bounces to the left or the right, you sort of keep track of, what happened. It doesn't have to be this particular example. Just in general, you think about at every choice that's being made, and as the simulator executes, you can ask, well, what's the probability you would have taken that particular path compared to the same path for a different setting of the parameters? And oftentimes this is calculable. Sometimes it's also possible that you can calculate the derivative of that, like the probability of a particular path. So you keep the path fixed, and you say, would this path have been more or less probable if I change the parameters theta a little bit? And if you can calculate the derivative of this log probability, which also often doesn't require knowing the normalizer, then this is also something tractable. So these two quantities we call the joint likelihood ratio and the joint score, you can often extract from the simulator. And then what that turns into is, if this horizontal axis is your training data X, previously we just had binary labels like signal and background, null and alternate hypothesis. So this is what the training data looked like. And we were trying to learn this red curve, and you can imagine that learning this red curve, this likelihood ratio, is going to be difficult if this is what your training data looks like. And with this augmented data, the training data now is scattered around the true sort of likelihood ratio. This is like, and so it's of course going to be much easier to learn. And this joint score is also giving you sort of tangential information. So all of this together is going to give you a much easier learning problem. And what we've seen in the context of particle physics is that this is essentially how accurately we're estimating the likelihood as a function of the number of training samples. And we see that we can do better with, this is a logarithmic scale, with several orders of magnitude less training data. Okay, so that's just kind of a, two examples, approaches to a broader ecosystem of possibilities. And I'm going to give some quick physics examples now. So in the context of particle physics, here's one of these Feynman diagrams that's producing a Higgs boson. These interactions involve the Higgs particle interacting with other things. And we have reasons to believe that maybe there's something interesting, some new physics happening at those interactions. And we can parameterize the effect of those, what some new physics might do with, with these coefficients that modify, the interaction at those spots. So we just have two, real valued coefficients that we want to measure. The data that we observe, there's a bunch, these are all different outgoing particles with energy and momenta. There are energy and momentum constraints. So intrinsically, the data is something like 16-dimensional, but we often use redundant variables. So we might have something like 42-dimensional data that we actually feed into the neural network. And this is something you're not going to fill a 42-dimensional histogram, right? So the traditional approaches would totally not work in this setting. And what we see is that we can approximate, this is the estimated likelihood ratio versus the true likelihood ratio, and we can estimate the likelihood ratio very accurately. And then this is the log likelihood as a function of the parameters we're trying to measure. 0 would be, say, the standard model. And so what we want to see is this log likelihood curve get as narrow as possible. And compared to traditional techniques, it's like adding 90% more data at the Large Hadron Collider. So it's like a substantially more precise measurement. There's been some other work along this direction. This is a 2-dimensional parameter space. The traditional techniques were saying we could measure, you would expect a measurement with an error bar that looked like this red dotted line. You want the error bar to be, the error ellipse to be as small as possible. And using the techniques I just described, you can move to this blue error bar. And so this is like, increasing the data by, several factors. And so for like a real flagship measurement at the LHC. We've also applied these kinds of things to dark matter. So here's a galaxy, and the little blue blobs this is supposed to be a halo of dark matter surrounding a galaxy. And the blobs are like what are called subhalos, like little clumps. The dark matter is not perfectly smooth, it's clumpy. And the mass of these clumps follows a power law type of distribution. And then that power law can have a cutoff that's sensitive to the mass of the dark matter. And so if we can measure, this distribution, this would be great, but the dark matter, of course, is invisible, so we can't see it directly, but we can indirectly get at it by using gravitational lensing approaches. So here's Earth, here's some background galaxy, and the light is being bent due to general relativity around this foreground galaxy. And you get these kind of crazy looking images like this, where the background galaxy has been lensed and smeared out in this funny way. So we're looking for little perturbations to this image that are going to give us a sign for what the clumps of the invisible dark matter around this this foreground galaxy might be. And there's going to be a lot of data of this nature coming up in the next few years. And so what I'm just going through this really quickly, but we have a simulator that first sort of assumes some power law with parameters that describe how steeply it falls off and what the total fraction of the dark matter is in these subhalos. We run through a simulator, and then we produce these kind of synthetic observations. So while we can sample from the simulator, the likelihood associated to this image is intractable. And what we'd like to do is turn this around and do, based on some images, do inference on the parameters of this power law. And so this is just some details of the simulator that I'll skip, but we include, Poisson, shot noise from the photons, point spread function that's like you expect in that particular Euclid detector, and various things. And once we put it all together, we have a pipeline that can eat in a number of images. And because it's amortized, we can do inference very quickly. And so you see here with hundreds of images coming in, we're able to isolate and put a posterior distribution on the parameters of this power law distribution, and they concentrate around the true value that was used for the synthetic data for this study. So, I'll wrap up now. So I think that this is like a very exciting direction. There are some potential weak points, which are that, for instance, you might worry, well, what if my simulator is not perfect? That's certainly true. Of course, that's always true when you do statistical inference. Statistical inference is always done within the context of a model. So on one hand, you might say that the simulators are the most accurate, statistical models we have, so we should use them. On the other hand, it's reasonable to be skeptical that there's, as you model more and more details, you have more chances for these methods to focus on something that's poorly modeled. So we need to be responsible, scientists when we use this stuff. And also there's the point that, humans are pretty good at designing robust summary statistics so that we don't focus too much on these irrelevant details. And for machine learning, that can be hard. But there are numerous approaches that are being developed now to try to get this kind of robustness into the machine learning pipelines. And so I just point to some of the different ideas that are being thrown around in that context. These next few slides I'm going to skip because of time, but we did put it into kind of a full experimental loop where instead of just doing inference, we thought about experimental design and trying to figure out, what experiment should you do next. There's some demos there, so I'll just skip that. There's the point here that in the broader story of the, scientific method, where these things are really useful for kind of like, gathering data and sort of testing hypotheses, but in the broader scope of generating hypotheses and things like that, and designing experiments, that's a place where AI is still not particularly strong, and so it is important that we maintain some notion of interpretability. The last thing that I had here was about there's a kind of another direction of work that has to do with when you design these neural networks themselves. How do you what kind of architectures do you use? And so there's a lot of work going on now about trying to come up with different types of inductive bias, different types of architecture that fit really well for a particular domain. And that often is related to sort of connecting to the causal mechanism about how the data is generated. And this is just pointing to a handful of papers that, and studies that have been done in that direction. And these are the kind of some keywords that I would search for in that direction. And so I'll conclude with that. And I'll just say that I think that, this is a pretty exciting time, and that machine learning can really help us get more out of these simulators and effectively provides a statistical model for the observed data that's tied back to the low-level reductionist picture. But harnessing the full potential of these techniques is going to require often augmenting the existing simulators. So for those of you that are out there that work on the software for these simulators, I would definitely look into this, because it's a way to just improve all of the downstream use of that synthetic data. And then I think, as a scientist, it's important that we just keep in mind that while machine learning is very useful, we really need to make sure that these systems are robust. We can try to make them be more data efficient by exploiting compositionality and causal structure and various things that we do know. And it's a pretty exciting area to think about how it is that we're going to inject and extract our domain knowledge into these neural networks. And with that, I'll end. Thank you very much. Am I still connected?
Yes, thank you very much for a great presentation. I just have a quick question about the causality part that you mentioned. And could you please expand a little bit on how you incorporate the causal structure of data into deep learning, if possible?
Yeah. I mean, at this point, I would say that that there's no like full like general magic recipe. I would say that at this point, a lot of the work that's being done is more a bunch of kind of specific examples. And as we do more of these examples, like we as a community do more of these examples where we take into account what we know about the data and how the data is generated, and then we try to come up with neural network architectures that seem like a good match, and we collect more and more evidence that this actually helps. You know, first that we can strengthen the claim that it's worthwhile doing. The other thing is we can look to see, does it make for a more robust system? And there are now like quite a few studies that are pointing to that working out pretty well. So in this top example here, what's happening is that, you know, I showed at the very beginning this picture of, in the particle physics example, we have we produce a particle that radiates, and then those particles radiate more and more, and it evolves in this tree-like structure, but we don't get to see that radiation pattern. We just see the particles that hit our detector. And so what was done in this example was a neural network where the leaves of the tree are the input, and those are like the particles hitting my detector, and the architecture is generated dynamically by using a domain-specific hierarchical clustering algorithm that we already had, that looks at all those particles and says, well, you know, these two are close to each other and some, you know, appropriate notion of closeness. And so I think I'll cluster them together, and then you repeat that procedure. So you get this hierarchical clustering. So we use that as the architecture. And then we put essentially little non-linear neural network components along the way. And then this takes in all of the particles and you feed forward, and then you get like the output, you get a, you know, single, say, classification decision, or more generally, you get like an embedding of that jet into some latent space. And this approach, you know, mirrors the picture that we have in our minds about how the data is generated. And the technique actually works very well. It has, you know, like orders of magnitude less parameters than like a, you know, many of the, like a ResNet or something like that would have. And then in some studies where we perturbed the data, these were more robust to systematic uncertainties and things. And it's just a conjecture that maybe that's partially because, you know, it's taking into account some of this domain knowledge that we know. And so some of these other things have to do with, for instance, graph neural networks, where, you know, you can imagine that you have, like if you're modeling, that's what this video was about, you're modeling this system of particles that are interacting, say, gravitationally or through some spring. So this is the ground truth dynamical system evolving. And we wanted to be able to predict the future of, you know, what would happen. And so instead of using like a neural network with, you know, like a feed-forward neural network with inputs that represented the like XY locations of all these particles, we instead used a graph neural network. And the graph neural network explicitly tries to model like the forces between those objects. And that worked out quite well. And then we were even able to like incorporate things like symplectic integrators and, you know, ODE integrators and things into the neural network. And we get these very, very accurate predictions and rollouts over like thousands of time steps.
Thank you.
Okay, can I ask a question now? I had
Sure.
Okay, great, thank you. So yeah, my name's Eric. Just turn on my camera real quick. Hi. Oh wait, let's not cover the camera. Okay, so thank you for the talk. It was fantastic. I mean, everything's fantastic. So I had a couple of questions. First, I was wondering if you could show us a slide again about the keywords related to inference, because my thesis is on emergent behavior and they all look familiar, but it was very quick. So.
Oh yeah, no, everything's quick. I can make these slides available so that you can see it. The review, in terms of inference, this review paper is probably what I would point you to.
Okay.
Yeah, and so it's published in the Proceedings of National Academy of Science, but it's also on the archive with this number right here, which I can type in the message box.
Okay. Gotcha.
Yeah.
Okay.
I'd be very
right,
interested to hear how that works out.
Yeah. Okay, so then the second question is, I'm just curious, given all the work you've done, how you would define emergent behavior.
Yeah, I mean, I'm using that like fairly loosely in the sense that what it could be is, not something super mystical or something, but just like a coarse-grained version of of what's happening, right? So you might, you might just have like if it was an image of some surface, you just have like, say, a low resolution image of what's going on, you still have this issue that the data that you're observing, you need to be able to integrate over, this the sort of microphysics of what's happening, the higher resolution version. So that's a kind of boring version of emergent phenomena. A more exciting version of emergent phenomena would be things like you see in condensed matter physics or something like that, or like a swarming behavior or something like that, where you might have, for instance, I don't know, if we think about COVID, like the low level information is individual people walking around, shaking hands and passing disease among each other. And the larger level emergent phenomena is going to be something like, do you have a pandemic, or do you have like a hotspot in some area, and how does it respond, and that kind of, and that's something that might be what's more observational. You might just have very, coarse-grained, large scale data about, for instance, the total, number of people in the hospital or something like that. But yeah, there's lots of variations on it. But I think sometimes it's just like a coarse graining, and sometimes it's something where there's really like a different, a different description is more relevant, with a different set of degrees of freedom and things like that. Right.
Okay. So can I ask one more question?
Sure.
Okay. Have you seen, I've looked, so, but have you seen any work? I'm really excited about graph neural nets. So for example, I'd love to see something like that where you can do a hypergraph. So it would be, the collection of interacting objects would then become the node in a higher level graph, and you can just daisy chain levels of abstraction. And that's kind of where, absolutely. So that's kind of where my thesis is going. I'm wondering if you've seen that before, or anything related to that topic, or the attempt. So yeah, kind of like what you were doing here. Yeah, exactly.
Yeah. So I think that, graph neural networks are a very nice fit for a lot of this discussion about, of separating scale, thinking around different scales and coarse grainings and things like that. And there is a fair amount of work going on in that direction. So I sort of point you to, some of these, but some of this was done in collaboration with DeepMind, and one of the authors there is Peter Batilia, and he is, he comes back from a background is actually about cognitive science, and a lot of the point that that he champions is this idea of compositionality, that you have that you have some larger object that's composed of some smaller objects, and that graph where you have multiple graphs corresponding to different coarse grainings is very popular, and there's they've done some work to try to demonstrate that in different contexts.
Okay.
Yeah, actually, Peter gave a talk yesterday on graphs.
Oh, that's right. Yeah.
Yeah, exactly.
He probably showed you some of his amazing stuff. Yeah.
Actually, I also had one more quick question. So with respect to graph neural networks, so can you map a causal structure onto the graph neural networks, right? Because that's, people map it onto DAG, but can you actually do some causal inference using graph neural networks?
Yeah, I mean, you can certainly, you can have that graph, and the graph can be directed, so there can be some notion of the causal direction if you want, and and then, once you have that, in some sense, that is a causal model for the data. Whether or not that's the actual the causal model that's actually underlying the real data is a different matter. But I think that what's nice about a lot of this is that with the inductive bias and these kind of graph networks is that it's very easy to take a scientist's picture about how things work and kind of encode it into a graph neural network, because like the nodes sort of represent some object that has some physical sense, means something, right? And so it's much easier to sort of tell the broad story, and even if it's not an exact map of what's going on, oftentimes the inductive bias of a model like that will lead to good performance and quite a bit less training data needed to be for training it. Oftentimes it leads to like more robustness to systematic uncertainties. But certainly like case by case situation. I mean, and if you have the wrong graph, of course, that's not gonna work. But
yep. Okay, thank you. Are there any other questions to speaker?
One more quick one.
Yeah, sure.
And I'll just combine the whole discussion because causality is everything. So would you happen to know maybe a couple of references in addition to the ones we've already covered where they're attempting to do both?
To actually discuss there's more work that I've seen that sort of assumes that that's the right causal model, and then either looks to see improvements in generalization or something, or more sample efficiency. There's also been some work in reinforcement learning by Danilo Rezende where he shows that if you need to take into account some of these like backdoor corrections and things in causality to be able to get your agent to learn properly, because there's a mistake that's happening from a causal perspective during the reinforcement learning process. That idea of trying to actually do causal inference to discover the causal graph is something that I'm very excited about. I think various people are thinking about, but causality, when you move away from discrete random variables, becomes a lot harder. So I don't know of any have something specific I'd point to that's like this is the answer, but I'd say that lots of groups that are doing cutting edge deep learning research are moving in that direction.
Okay, thank you. Thanks. I guess we have emails. I have a million questions. I know I have to stop.
Okay. Yeah. I can try to point you to some things later.
Okay.
Okay. So we want to then convene for lunch, get some food, and the tutorial start at 2 p.m.